Welcome for the attendees that have joined our webinar this morning. Welcome, and I think we will have a lot of good insight into thermal imaging with injection molding and how to control and monitor your process. So I think you guys will have a lot of good information from Kenny in this webinar, and I'm sure that you guys will have a lot of questions for us, and we'll be happy to answer those at the end of the presentation here. But to kick the webinar off, what we'd like to do is just try to take a poll of what industry are you currently in, and that helps us really understand kind of our audience and who we're talking to. So I'll give you about 30 seconds or so to select one of the industry checkboxes, and you can submit that. We'll see the results come in shortly. Okay. Looks like about 80, actually just jumped up to 90% of you have voted.
I was going to say, so anybody who has selected other, if you wouldn't mind in the question section, just filling in what industry you're with. We'd be very interested to know.
That's a good idea. Thank you, Amy. So I'm going to close the poll. Looks like about half of you are in the automotive industry. We have some in the consumer products, a little bit medical, a couple in furniture, and the other half in others. So looks like someone's here from aerospace, which will be good for us to understand. But yeah, if you could submit your industry and the questions, we'll try to arm that so that we can address you accordingly. But that's good, and again, appreciate you guys dialing in for this. So, knowing that, what we're going to start with here is what is thermal imaging and how does it work? Now, some of you may already know or are familiar with this technology, but what it is, we use long wavelengths of light beyond the visible spectrum. Now, generally, we don't need reflected light. This is energy that is emitted from an object, and we have three main types. We have reflected energy, we have emitted energy, and we have transmitted energy. And those are all the different wavelengths or the types of energy that the camera, the thermal camera receives, and we're able to make decisions with that information. Our best or what we really like is emitted energy coming from the object. Reflected, we try to ignore, and that could be from objects with other heat, like a lamp, overhead lamp, or another piece of equipment reflected off the object. We're not really concerned about that. And then there's a little bit of transmitted. We do use transmitted energy in our analysis. But what is this electromagnetic wavelength that we're talking about? It's a longer wavelength than white, and it does follow a lot of the same physics as the other spectrums of light. IR is emitted by all objects, as you guys are aware, and it's really how it works is it's the generation generated by the vibration of molecules. So the faster that molecule is vibrated, the more energy and heat it produces. So yes, we can see cold objects with thermal cameras, but it produces less energy out than something that's much warmer that we can receive. So that energy it passes through the lens of the camera, and those photons impact the heat detector element in the camera. And through some advanced calculations in the thermal camera, we're able to get a bunch of temperature values, independent temperature values. And we present that to you in what's called a thermal image. Each one of those pixels are designated to a certain temperature, and we assign a color to that, and that's how you're able to see that thermal image. To give this some context, having a thermal camera at 640 by 480 resolution or pixels is the equivalent to having over 300,000 individual pixel points or temperature measurement points. Consequently, it's like having over 300,000 thermocouples or pyrometers. And we're able to use and correlate that data, again, to make some pretty advanced and calculated decisions in manufacturing processes. So Why do we want to use thermal imaging technology? Well, we do 100% product check on each machine cycle. We're able to use that thermal image to detect problematic issues in the manufacturing process. It is consistent, it's reliable, and now we're measuring not only the consistency within maybe a particular part, we're able to run part over part over part and check for those consistencies as well, identifying inconsistency or ununiform thermal profiling. We measure the heat signature on the entire part. We're not looking at a particular one spot measurement. We're looking at the entire thermal image and doing the analysis. You'll learn here through the presentation that we can be fully integrated into the equipment for automated decision making and bidirectional communications with the equipment. And this is a quality assurance piece of or process or a piece of equipment. Really, our solutions powered by Enlighten software are able to really give that assurance and peace of mind that something is checking your parts for quality each and every cycle, machine cycle. So I'm going to roll into another poll here. I want to ask, do you struggle with objective visual quality calls on your part defects? Let me launch this. Here we go. So yeah, so do you struggle with the visual quality calls? So if you're looking at parts and your quality office is having a look at those parts, do you have objectionable calls on whether what's good versus what is bad? And we'll give about 30 seconds to answer this question. A lot of people or quality or in plants will inspect one part a shift or maybe a batch of parts a shift, and based off that inspection, if they find one defect, you really have to look and check the whole lot and pull that off the line. And I know it takes quite a long time to do those inspection points. Furthermore, a defect could pass with one inspector and fail on another. So that's, those are some of the things that we've seen out there in the industry. So I'm going to close the poll here, and the results are yes. 80% of you said yes, you do struggle with some of this. 20% say that you do not have any issues with independent quality inspection. So based on that, that's kind of where we really fit into this light. For those that do struggle with that, again, we're looking at checking every part during the manufacturing or the assembly process and making those calls in a live inline event. So what we have put together is what I'm going to call an ecosystem. All right, it's just a thermal machine vision system, and it's what we term is a thermal process monitoring solution. Really, what that ecosystem consists of are the FLIR automation thermal cameras into this thermal process monitoring system, which is powered by Enlighten software. It has bidirectional communication protocols to communicate with the PLC and to make those good versus bad calls. And we have remote interfacing with one of these systems. So it is a full, complete, integrated, turnkey solution. These infrared advanced solutions are powered by Enlighten, can provide quality measurement solutions for injection molding, which we're talking about today, but a lot more, right? We can do plastic joining, adhesive validation, thermal forming or compression molding, and vacuum forming. We do a lot of condition monitoring, predictive maintenance, process control, so on and so forth. There's just a very wide host of solutions. But today we're really going to be focusing in on injection molding and how we integrate this really advanced technology to monitor and have a look at in quality control and injection molding processes. I know we've done a lot of polls, but I'm going to ask you one more here. Do you struggle establishing root causes for your defect? So let's say you have a defect and you're trying to figure out what the root causes are. And this in industry is quite a problem that we're faced with. We can see an injection molding process, maybe some splay, or maybe there's structural defects or integrity issues on the part, and we're really trying to figure out, was that the material, was that the heating process of the mold, was that the cooling process in the molding? We really don't know, so we start just turning dials and changing things in the hopes of landing on the solution of that process. So with that, it looks like, of course, 80% of you, or 82% said yes, we do struggle with that, and 18% say no. So this is something that we'll address here, that Kenny will address in his part of the presentation here. So with that, I'm going to pass the technical side of the presentation over to Kenny Renicky. Go ahead, Kenny.
Okay. Well, welcome to all, and I'm not sure exactly how many people there are there, but there's a lot, I guess. And we appreciate you joining the webinar. Like I said, I'll be talking about injection. There we go. Okay. I'll be talking about the injection molding portion of this. And anybody who's been in injection molding knows that it is a heat in, heat out process. And how much heat you put in and how quickly or evenly you take it out is going to give you your final product. And whether or not it's dimensionally correct, without warp, and if it has the aesthetics that you're looking for. So as I've worked with many different type of systems and monitoring systems over the 38 years that I've been, 39 years of doing this, I remember I've got my first enlightenment when I was saying, wow, now you have pressure monitors and tools, and that's really great. Now I can see inside the mold where I couldn't before. But never before have I had the breakthrough that I've had with the FLIR cameras to be able to look through the entire material path and see exactly what's going on and going into that part and what's coming out of that part. These cameras are absolutely just, for me, just a whole bunch of fun. So as I look at the product and the quality of the product, there's what I like to call the 4 horsemen of the apocalypse that will get you one way or another. But we're going to talk about your flow rates, your plastic flow rates, how fast you're doing your injection mold, and that will also give you your shear rate and how much heat you're creating through that shear and how long that shear length might be. We have your plastic temperature itself, which can be done by your heater bands or your mechanical shear you've got for RPMs of the screw, compression of the screw itself ratio, whether you got a 2-to-1 or no purpose type screw, or you got a high compression, what kind of back pressure you're trying to do to get a homogeneous melt in through that, all which give mechanical shear into the product. And those different types of mechanical shears are all conducive to how well your material is formulated from your material supplier. In this, they put a lot of what we call heat stabilizers, or bodyguards, as they say, for the molecular chains, flow plasticizers and those types of things, and then fillers, and you have all types of stiffeners and talc and that will be in there. And all those will affect all these different, what we call 4 horsemen of the apocalypse. Cooling, of course, is key as well, and you're cooling that it's working properly in your mold as well to be able to take that heat out at the proper amount of time. And then the pressure that's involved in that. Your pressure gradient, do you have the proper amount of pack? Do you have the proper amount of fill until you get into secondary pack, that you have the proper densification all around the part? If you don't densify properly, all evenly throughout your part as you put your pressure and packing into it, what you'll do is allow for some slippage in that cooling rate, and you get a chance to get your warpage that comes into play. So as we look, thermal imaging is a excellent way to be able to keep track of what's going on in all four of these particular areas of the molding process. Okay, so here's a simple little picture we came about, and please feel free as we go along. These are all very simplified to try to keep Kenny from talking too much and making this too long. And Kenny's got many presentations after the fact that he can send you that have a lot more description and a little bit more for the guy who wants to know even more why, right? Love the guy who says why. I'm not the same type of guy. So we analyze and control the molding processes as the heats go up or go down. You have good melting, homogeneous melting or lack of it, or you have thermal degradation, which can give you shears and burning and all those splays and blushes and things that we don't like. As the pressure gets too high, we know we get to the flashing issues. Go too low, we get to the short shots. And of course, in between there, depending what the mix can be in there, you can get that warpage that happens as well, and how well you are doing all the above as you think you're doing. So that would be your shrink rating through there. Thermal vents must be consistent to achieve proper dimensionals, eliminate issues such as part warpage, mold stress, size, and visual defects. I know that sounds like a very simple phrase, but when we asked you before about, do you have a problem with making visual calls? And I was laughing to myself, like, I always think of the guy comes running up from the floor saying, let's take it to the quality manager. He's going to pass that. He'll ship that, because we always would say, I think this is good. No, I don't think this is good. It's the quality school of Goldilocks. This one's too hot. This one's too cold. But it does get irritating. And ultimately, some of those decisions come into play of the need of how bad you have to ship the part, unfortunately. But what we talk about here is, if let's take a knit or a sink, and if we have recorded in through there what is the best process, we've done a DOE, we know exactly what the perfect part is, and it's supposed to be at 175 degrees on one side of the knit line, and it's supposed to be 174.5 on the other side. And if it's not, and then something's wrong different that's happened in the flow or whatever the material that you're getting from your material supplier has changed, we'll pick it up right away. And we'll be able to know through past data as we run thousands of your parts, and we'll be able to get the statistics of your part, what your 3 sigma should be, and be able to tell you with any confidence whatsoever that that is a good part, like it was last week, or like it was on first shift on first piece inspection, and it was last week on first piece inspection. Or we'll be able to tell you something's changed and give you a direction there. Okay, that was a lot in a mouthful there, so I'll try to hit this one. Okay, so how do we know your equipment and each mold is operating properly? Like we've talked a little bit, one of the first things that we'll do when we get with you is we discuss your part and all about the quality. What are all the different types of concerns that you have? Historically, what are things that go wrong with that? And in those discussions, we come up with ROIs. Those are reasons of interest for us. This is where I always inherently get a sync mark. Okay, so we'll take a little box in there and that's going to be a reason of interest for us. We're going to want to know exactly what that is. And we're going to want to know what all the different mold drop temperatures are and going through the gates and all those type of things, mold temperatures, areas in through the manifold. We're going to go and pick all across on your part areas of regions of interest that means something different all across your machine and all across your mold that we can pick things up. One of the big things, I don't know if I should have made this a poll question, but if anybody struggles with vents, and I think maybe we might even consider that at one point, but vents are something in a tool where as the gas builds up, as you're processing your plastic, it has volatiles, and those volatiles are released from the plastic itself and then get pushed out through to an area of last fill or end of fill, and they have to be evacuated or vented out from the mold. If in fact that venting is not working properly, it can actually cause burning or non-fill areas because it resisted the keeping the air inside, and it superheats right in that last condition. What it also does is before it closes off that vent, the first thing it will do, it will start to make a little gummy type residue. Some people call this defect in the plating world called juicing, where the gases actually condense so much, the molecules condense so much, they turn into like a liquid or a vinyl. And that's what first starts to block your vent and starts to give you your very first shot at your quality problems that you're going to have venting problems shortly. We can pick up when that's starting to increase in that heat and when you're starting to say, you know what, you're clogging your vents right now, so I'm going to tell Joe on first shift via text, it's time to stop the machine and wipe and clean your vents. Instead of saying, well, let's go ahead and clean it at the beginning of the shift and let's clean it at the end of the shift, or taking arbitrarily when do we have to clean that actual vent. It's nice to know when exactly you need to clean that vent, because the material that you're getting will vary at all times, and sometimes it will gas more than other times. So one of the areas we like to pick out and see how well your vents are going, so whether or not to be cleaned or need to be opened, or just by watching your vent areas, those are areas of interest to us on the tube, on the tool itself, as well as areas where your water flow will be, to make sure that we're getting proper Reynolds numbers in through there, and that you're consistent through all your water lines and things aren't starting to get clogged up, depending on what part of the country you grab your water from. They could be filled with a lot of minerals, and those areas can get pretty stopped up if the maintenance isn't keeping up with the acid etch on the tool. Okay, so I kind of went through a lot through there, but those areas of influence are sat down with all you people, looking at your mold design and discussing all your entire process, your vents and everything else into your setup. And we will determine what is important for you to be able to determine where to go when you do have a problem, that we indicate that the temperatures and things are starting to change. There has been some variation. Okay. This is we have a two-cavity plaque tool that we have here at our R&D center. We'd love to have you all down here. We can teach you all about the thermal cameras, how they work. You can see it in this mold that's sitting right in front of you. This mold itself has several things that we can play with in here. It has inserts for, it's a two-cavity sequential valve, 4 drops. It has interchangeable gates that will give you from 40 to 60 to 80 thou thickness of gates. That dog bone that's in the middle there, there's also 2 on the outside. Those are standoff pads that we can add a couple thou for venting and show you when the venting is starting to clog. If we put a thou in, how it gets rid of and takes care of the closed off vent problem. There's many things that we can show you with those nozzle temps as we go up and down and delay them to simulate any kind of problems that you would have on your process as well. And we could also teach you in our offerings, we want to make you smarter so we can get more cameras out there so you can control more of your process. We also do DOE teaching here, where we'll literally take you through the science of DOEs with Wisdom software and the FLIR cameras. We'll set these up together. We'll run it piece by piece, and we'll evaluate it and be able to show you exactly how we can monitor, fix, and control every part of these plaques, and actually make the plaque whatever dimension we want to make it to by just estimating through the DOE software. So that's a lot of fun, and if you're a molder like me, and you really like to see the science and data, and more data, and see it in numbers where you can walk away and say, it makes sense to me now, I get it, it's in that Excel process there that you got, and I can look it up again, and now I know exactly what affects my part. Those are great kind of powerful tools to have. And again, thermal imaging has done so much for me as far as letting me know what's happening on that part and that tool as a whole. Okay, so we would go ahead, and these are some of the process ROIs we have. You notice I'm looking at vents, I'm looking at mold temps, I'm looking at melt temps, I'm looking at nozzle temps to make sure they don't move. I'm looking at what's coming right through that vent right there to see if I'm getting more shearing. This happens often where the shearing starts to pick up, where they start to lose in the formulation, especially when the material suppliers move into transitional grades in the reactor grade type materials. and they start to lose their bodyguards or their anti-heat, heat resistance, and all of a sudden you'll pick up, you'll start to get a lot of shearing all of a sudden that you normally wouldn't be getting out of your gates, and that's where you get that spotty splay and blush that comes and goes and haunts you, and you don't know why because nothing's changing your process. Well, that's the first thing we can pick up right away. Make sure that you're shearing like you're supposed to be shearing. You're not picking up some nuisance type shear heat from it. Okay, let's see what else I got next here. We had to trim this down for a lot of slides so we didn't get too many, but okay. It says, do you struggle maintaining venting in your tooling scenario? I thought we had this question. That's good. I'll be curious to see what everybody says. And if there's maintenance guys in here and they're going to say, oh, yeah. Okay, so it looks like we got it's about split. Yeah, it's about split. And sometimes you don't even know what you're struggling with depending on what your job function or what you are, sometimes you're not sure if you do or you do not. Um, to me, I found it to be extremely important as far as knowing when my vents are starting to go on me. So I can keep them clean, not only on the maintenance end, keep them open, but keep them clean from the buildup. Okay, thank you very much for participating on that poll. So how it works. The cameras, they're quick, they're fast. They capture an image in 0.2 seconds. The data is collected and temperature reasons of interest that we just showed you in 0.6 seconds. In that amount of time, so a total of 0.8 is what we're going to ask you for to sacrifice in your process, and we'll be able to give you a decision based on a lot of data. And we're going to be able to tell you one of three things. Basically, it's good, it's bad, or you know what, I want you to look at something. This is important. Sometimes we'll look at something where we say, you know what, if we start to trend X amount in this direction, we'll warn you to say, maybe you should check something because something's starting to just trend on its way out. It's not a reject. However, we want you to check something. And there are other times when you just don't want something in the hands of an operator making a decision. I think what I love most about this, depending on how far you want to take this, I know in the chrome plating world, we had to be able to put a barcode on every single part. And at any given time, when it was being processed through the plating process, we were able to look exactly what happened to that part in the process and all the tanks, some of it for safety reasons. And we had that traceability for years and years and years. So anytime when there was a part in question, we could look it up. Same here too, depending if you want to tie it to a part number or not, or the time, we can store that information and keep it for you at all times, showing traceability to that part was good and that it went through your process and where it's supposed to be and all your temperatures were in control. That's powerful nowadays with the customer, but it also helps me sleep a lot better knowing that those decisions are being monitored by somebody a lot smarter than me, who maybe doesn't get moody. Okay. So we got another question. Do you have a Pokio system automating your process right now? Do you have somebody helping you make those decisions? I remember back in the olden years, it used to be that every time there was a quality problem, somebody would come in with a part to my desk and say, what is this? Can you fix this? So I was the Pokio, the problem solver, everything right from behind my desk. That was kind of a pain. Okay. So it looks like 86% of you said no, huh? Okay, you got to buy this stuff. No, I'm not a sales guy. But I'm going to tell you right now, and probably is the reason why you are listening to this webinar. It's very dangerous and sometimes can be costly. And the worst thing that you want to lose is your reputation or missing shipments. And without having that safety net to make sure that things are not going out of control, it is really important to have these type of POCIO type systems to assure you that you produce that quality and expectations every single part. Okay. All right. So unwanted process changes, things that how can the thermal imaging show my process engineer what change is occurring? So how is it going to point him somewhere? A lot of that we can talk about a little bit. And I really would like to take a longer presentation to tell this in more detail, but there's several things about the basis of the physics of flow that we have to understand, the plastic flows and the plasticization process. There are things you got to keep in mind that plastic will always repeat itself. Plastic has a memory. And plastic will also come from one area and map itself from one to another and repeat itself from one area of the material path to the other. Fountain flow, you have to understand that the plastic itself, it does not push through the mold. What it does, it flows out like a fountain, and it goes in between two skins, between your cavity and your core. And depending on what that speed is and how thick that skin is, it will pick up some frictional shear heat as it flows between those two layers. And if you get with me later, I'll send you a video that was made by GE that had some colorant put into that thing and show. Oops, sorry about that. I just moved my had some pigment put into a clear glass mold where you could actually watch the fountain flow of one pigment being flowing into another underneath it. It's pretty fascinating if you've never actually seen it, to show that fountain flow really does happen in a real way. What we talked about for dynamic redistribution or rectilinear flow is basically at any point during the process, in that whole process material line, as I look back through here, let's say I have a zone, if you look all the way to the left, they're all in yellow, everything's good. All of a sudden I lose one of my zones up on the front. What it's going to do is it's going to affect the very first plastic that's in that first one being loaded up. And then as that hot shot gets brought into your mold, I'm going to pick that temperature up. And it's going to keep on repeating itself depending on how many shots you have in there in that same spot, saying that zone's out of place. Now, how do I know where that zone's coming from? When I come to your plant and I go ahead and we do the scientific setup, I look and I know how many shots are in your barrel. I know when I do my shot analysis and how as it goes and fills every half inch of your bar or every quarter inch of your barrel, exactly what that means on the space of your part. So I'll be able to go through your whole mapping, knowing through whether it's your thermocouples on your barrel or whether it's thermocouples in through your manifold system, where those hot spots will be coming for, to point you in a direction of where to look. Not just tell you it's in your barrel, you got a problem, but yeah, you got a problem with the heater band number 3, zone 3. So these are some of the areas that it tells you right away what's happening. It's the same thing if I was looking for an area on your mold. Well, the mold is getting hot. Where is it getting hot? Well, on this line right in through here. Oh, that's my water line number 3 over through here. And go ahead and you take it out and you look, you blow through and you say, holy Moses, I'm not getting any flow through here. It's all gotten backed up. Or I had a diversion plug that slipped and now it's not rerouting, it's actually blocked off the water. It can pick this up actually specifically where that particular area is. And I'm probably being told to hurry up a little faster here because of the amount of time we have. When I talked about that rectilinear flow, that basically tells you that during in a barrel or fill system, every part in that manifold will come out in the same spot, shot after shot after shot. If you look at the way this thing's laid out, that's the way it would lay out coming from that barrel, from electrical flow back into the edge-gated piece that you're looking at right through there. It distributes itself repeatedly each time. So you know where that's coming from. So why do we have variation? And what is the image going to help us with? Well, there's only really three ways you have variation. There's three causes that are happening to you out there. The first one is that variation in the plastic rheology from the material supplier. Now, we have all this stuff that we do and all these things that we check, and we buy our material. I'm just be curious, and when you're done with this, ask your people, what size lots of material do we buy that I'm looking at? Is it 200,000 pounds? Is it more than that? And then how much of a qualified sample do I get? Do I do a melt flow that's certified maybe on one little sample out of that whole thing? Well, I can tell you that these materials that are being made in these reactor grades that are very like 2 metric tons per every half hour, and they're moving from one grade to another with less or more talc or whatever their offerings might be that they have to their customer, that the variation of that plastic, if you would be able to take a viscosity curve on every single one, would be amazing. If you ever had an RJG section system where you have two different pressure transducers at the beginning and the end of flow, that's a poor man's rheometer, and it can give you the viscosity of every single shot. And if you'd studied that over any given plastics, whether it's ABS, PC-ABS, polypropylene, you will find that there's up to 30% of change in a full lot of material at any given time. This is coming from your material supplier saying that it's perfect. And if you want to trust a material supplier, you are a very trusting person more than me. But that's what's causing you all your variation that you don't understand. What's going on? What changed? Is the process set up right? Yeah, well, something has changed. Your material's changed. Your viscosity has changed. It's either thicker or thinner, and something's going on. The other things that can happen are the malfunction in the plasticization process, and that's some of the things we talked about and we'll show you. You have a heater band, you have something stuck in your nozzle, you have water that's not working. Okay, that happens. Not as much as the other one, not as much as ongoing as the plastic, but you will have things in your process that will start to have a problem. Okay, that's the second kind. And the third one is when somebody goes and actually changes something. And maybe it's a result of they tried to change it because there was something above, whether it's the process or the material that they tried to make an adjustment for. And then when it went away, it made it even worse. So they're outside of where they were before. They tried to do a good change, and maybe it wasn't the best thing. But these are the kind of things that happen to us that when we get down that line, we say, what is changing? What is changing? You want to know exactly where and what is changing. Thermal imaging is the same every time. It will tell you there's something going on. You got all your material heats right, you got all your molds right, but you've got a shear problem. Your plastic is different. So right now, as I look at your melt temperature, it normally runs, for instance, take an example of 230 degrees. And now I'm running a lot that's running out here at 235. Okay, that plastic needs to be adjusted. Now I can make 5 different turns, or I can tell myself, okay, I got a thicker or thinner plastic. And if it's a thinner plastic, then I would say the easiest way to make the one adjustment and keep it simple when I have varying plastic going on, if it's not shear related, then I just change my melt temperature and lower my heats all at once and just watch that temperature and see what happens. There's several ways that we can give this, your process person, a direction map, troubleshooting guide, and anything that goes wrong for your areas of influence. And we can discuss that when we sit down and pick them and what we do and when we get our results. So I know I'm getting close over here. Here's one, this was a washer ring. If you look at this, basically you're looking at 2 rings with some inner pictures of those half moons. But what you're trying to look at, those 2 circular rings. The one to the left has a much darker orange up at the top. The one to the right has bright orange all the way around. This was a stack mold, and that's why you see 2 different rings in like that. But this was a stack mold that had 4 drops onto it, and these people would start up and start molding their product, and they couldn't understand after an hour down the line when they let their parts cool and why they had this warping going on. It's because one of their nozzles got clogged up, and that was the one up on the top on the left-hand side there. And so we had started to run this, and that second shot said, "You got a clogged nozzle." They said, "No, we don't. It's a full part." I said, "Well, of course it's going to fill. You got 4 different parts filling in through here, but you've got one nozzle that's not the right temperature. It's coming around from the other ones." And I said, "Let's go take a look at it." Sure enough, it was clogged. And after that point, once we got them running, they never had a nozzle clog problem, which was their main problem. They didn't even realize it. And their quality went through the roof. Their consistency went through the roof, and they had 2 parts like this, an inner and outer, that had to be dimensionally correct, that were spun well together for a washer unit. And we had cameras on each machine, the upper and the lower. We kept them dimensionally purposeful, spun them together, and they never had to wait. They knew right from the start whether their parts were good, and they always passed their leak test. So it was a fun project, a lot of fun, but it's the power of the temperature that told us right away. Okay, so what do I got? In summary, we know that thermal imaging measures emitted heat, as Roy gave you a pretty good introduction to. That injection molding is a heat in, heat out process, and how much you put in and how quickly you take that heat out and consistently you take that heat out. And the consistency of that heat is important. We have to have all these parts correct, and we have to have them for dimensional dimensional integrity, and to avoid warpage, and to have the aesthetics that we're looking for. Injection molding has fountain flow, generates a significant amount of shear heat into your process. And you always have to be aware of how long, when you design your part, how long your shear lengths are going to be and what kind of shear stress they're going to give you. I know a lot of people use mold flow. I use that as well. That's a good indicator of what's going on as far as looking at your shear stress. Injection molding is a repeated process, and that it will repeat itself with dynamic redistribution, so that you'll always know when you're looking at something going wrong in your part in one particular area, it's coming from one particular area in your process, and it's going to repeat itself over and over and over. So that's the key. Learn to know your thermal images, learn to know your areas of influence, what they are, and go immediately to when they're telling you there's a problem, and go right to where your variation is and fix it as quickly as possible. So I hope this will help you solve some of your business challenges, and I hope that this has been interesting. Sorry, I've been known to talk just a little bit too much, so now I'm going to turn it over to Amy. I think she's going to field some questions if we have some.
I want to thank everybody for their participation today. I hope you found the session very useful. Thank you for your attendance and your participation. Have a great day.